Welcome. Good morning. We're going to see control systems. The control systems is a system in an arrangement, collection of circuits, collection of systems, units. It may be interconnected units or distributed units related so that they form an entirety and they are defined by a term called entity. This is the definition of a control system. The control system has got a lot many physical components, distributed components, circuits, then units that can be integrated into a system, and the control system can have a single control system or a multiple control system. In engineering, the control system needs some special focus on mathematics. There are mathematical concepts pertaining to linear and differential equations, the Laplace transforms, stability circles, transfer functions, then signal flow graphs, then algebra related to transfer functions, that is polynomial manipulation using transforms, and the Nicholas chart. Nicholas chart is an advanced chart which is a plot of phase angle and magnitude. Magnitude which indicates the stability of a particular system. The stability of the system can be derived from Nicholas chart. It contains the phase and magnitude plots. Then it involves the analysis of root locus, circle root locus analysis, and real axis arrival angles. All these are important for control systems analysis using paperwork as well as hand derivations. When you say locus, locus pertains to a point in a complicated figure with which the entirety of the figure is described. This is called as a locus, and there is another term called as an asymptote, which will come for parabola, hyperbola. These asymptotes are very important for designing these structures. The structures are mechanical structures, and in structural engineering and mechanical engineering you can see all these mechanical designs. But here it is not about the locus which is pertaining to the complicated figures, but what the locus indicates, the points away from the loci or points away from the asymptote, they are going to indicate some errors or some instability in a particular control system. This is what we are going to see in a numerical and diagrammatic representation of some derived quantities from polynomial equations. Control systems, as I said, it is a different stream which can impregnate itself into many engineering streams, namely electronic engineering, mechanical engineering, structural engineering, industrial engineering, aerospace engineering, etc. The linear constant ordinary differential equations have to be studied for imbibing the concepts of control systems, but these equations are entirely mathematical concepts. They have to be studied in mathematical subjects, or they have to be studied separately in addition to concepts of the control system. The exponential curves, namely when we have an exponential curve like x equal to e power minus t, this particular term can be drawn in a graph as an exponential term by putting values for the coefficient, that is x equal to e power minus yt. This y can be substituted with some value, and then it can be plotted in a graph. This is called as a simple equation, but the equation may get complex when it comes to a series, binomial series or exponential series. For example, we can say instead of x, we will have y as the longitudinal axis and x as the transverse axis. In that particular fashion, we have y equal to e power minus t plus e power minus 2t plus e power minus nt, where n can be substituted with some term, and this exponential complex term cannot be directly plotted in the curve. It will give rise to some complex curves. This involves some numerical computations. Hence, to avoid this plotting analysis repetitively, time-consuming process, we have the transforms which can directly convert these terms into S-domain. This S-domain is a good indicator of a particular value. If we want to arrive at a particular value of where this plot will occur in a XY graph, then we can directly take the XY domain, which is pertaining to S transform, that is Laplace transform. Laplace transform is also called as the S transform. The S gives us the particular position of the value, which is derived by substituting some terms in a plot. This is being achieved. We cannot call this as direct frequency domain. Frequency domain is interrelated to some complex coefficients which are manipulated and arrived at some frequency domain. This is not entirely frequency domain, it is a linear time domain, but somehow we have the complex polynomials, for example, z equal to x plus jy, this is a complex polynomial. This is being called as a frequency plot with a complex polynomial, but we cannot directly relate Laplace transform with the frequency domain. This is an indication that Laplace transform is a starter for frequency domain, but it is not wanted. Laplace transform is best suited for space domain as well as frequency domain. It is an indirect representation of the space domain in terms of frequency domain. You cannot call this as frequency domain. We have the systems evolved from linear differential equations as first order systems, second order systems, and n order systems, depending upon the degree of the polynomial and the order in which it is being arranged. For example, the differential equation may look like this: d squared y by dt squared plus some coefficient a dy by dt plus by equals some constant. This is a differential equation, but the order and the degree of the polynomial is going to make it complex, and it will no longer be a singularity function. This is going to be complex because of the term on the right hand side is going to be again a term particular to time domain and the time space. Hence, this time space can be called as a real time signal, which can also be manipulated by a series. Real time signal is manipulated into a series by taking these order equations, but this order equation will not get directly give a series. This has to be manipulated into a series, and then with the series we can even generate a particular signal in digital means. This is digital means. It is not related to computer system yet because of the explanations that have to be involved in the ongoing process. Laplace transform is for many types of signals. For example, it can be for a unity signal, it can be for a constant, it can be for an exponential signal, it can be for a sine and cosine type of signal, it can be for some damped natural frequency signal. So Laplace transform, the main purpose is instead of plotting the signal in a real-time manner, we can convert it into S domain so that we can arrive at a particular plot when we know the spatial domain exactly. And this is related to frequency as well. But if we eliminate the particular value in the spatial plot, this is equivalent to removing the noise in the frequency domain. This can be done by the Laplace transform, but it is very complex. Human brain cannot do all sorts of noise removal at once, like we see in the frequency domain. In the frequency domain, it is very easy to filter out noise, but in the S domain or the time domain related functions, it is very difficult to analyze noise. And before going to what is noise, it is very advanced concept. We need to see what is the system comprised of. It is comprised of some equations related to mathematics, and it is comprised of blocks depicting the control system in terms of some functions, in terms of some manipulators, in terms of some integrators, circuits, in terms of some differentiator circuits, or in terms of comparator differential amplifier circuits. These are integrated into the control systems. We will see now a stability criterion in mathematics. It is going to determine whether it is a stable system or unstable system. We have a complex polynomial s cubed plus 4x squared plus 2s plus 2 equal to 0. This is one complex polynomial, but this has to be resolved in some real parts and imaginary parts of the system. This can be divided and it can be derived into some roots. When we have a polynomial, definitely the polynomial has got some roots. A complex polynomial with degree n has got n minus 1 roots. That means we cannot exactly say it is n minus 1 roots. It is the maximum number of roots. But the complex polynomial can also get minimum number of roots. Such a polynomial will be very stable. The complex polynomial with minimum number of roots will be very stable. However, the complex polynomial with maximum number of roots, that is, the roots do not exactly describe the polynomial well, will be non-stable. However, whatever we saw, s cubed plus 4s squared plus 2s plus 2, when we resolve it into roots and real and imaginary parts, you can see that there is a root table. Root table is one particular type of construction wherein it can fetch the roots as well as real and imaginary parts separately, and then it can indicate whether the system is going to be stable or not, depending upon some criterion called the root criterion. We have the polynomials described as we saw the root criterion, the root table as a concept which is going to describe. Still, advanced concept of stability is going to be in the form of resolving these polynomials as MATLAB or some MATLAB tools do, as taking these coefficients as matrices and then getting the eigenvalues or determinant values from it, and from the determinant values we can say whether this polynomial is going to be stable for a particular value or not. This is being done in terms of some characteristic equations relating determinants with the coefficients of the polynomial. This is one advanced stage than the root table criterion. There is one more advanced stage than the matrix and eigenvalues, which is the exact frequency transformation. So first we have transformed these particular polynomials into S-domain. This S-domain can be related to frequency transformation. Frequency transformation is very powerful, and we have a term called as a transfer function which is going to relate the output and input of the system, particular system, and the frequency response can be plotted with the transfer function. This is very powerful in analyzing the system, and it will give the frequency response of the system and the behavior of the system for varying the input signal frequencies along with noise. So we have the time domain representation of these particular systems, and when these systems as units are interconnected in cascade, then the same parameter can be multiplied and then derived as the output. This is the advantage of the multiplicity and cascading of the control systems. However, we have a concept called as the feedback. The feedback, when we do the cascading, it is not going to be stable system, so we have a feedback wherein some portion of the output is fed to the input in a proper controlled manner through a subcircuit. The subcircuit is going to sample and it is going to mix the particular portion of the output signal with the input signal so that it can carry out some error cancellations, or it can even stop the entire output of the circuit. This is possible by controlling the circuit remote. This is called as a control system with some controls defined by the feedback path. And we have the signal flow graphs. Signal flow graph is an algebra. This is going to relate the signal coefficients. When we have the polynomial system representing the signal, it is going to relate the signal coefficients in terms of a numerical graph, but this is not sufficient for the entire system. When the system is integrated into a whole, this signal flow along the path of the system is going to be determined by the signal flow graph. This is the advancement in the signal flow graph method. But for single unit analyzing, the signal flow graph is not going to help. The entire complex system is going to be resolved in a polynomial with different coefficients, and these coefficients can be plotted as a mark for the system in the signal flow graphs. For example, I can say resistors in cascade, an RL circuit, RL circuit in cascade forming a ladder. These can be analyzed into a complex polynomial. The polynomial is resolved into what is called as the transfer function. Then the transfer function is going to determine what happens to the particular circuit. But how the signal flows at each node is analyzed by the signal flow graph with respect to the nodes, number of nodes defined in the particular graph. We have a very important analysis which is going to be advanced in the control system. We have a finite polynomial. As I said, control system is going to be analyzed in terms of numerical methods as polynomials. They are no longer going to be analyzed as distributed units as to see what is the input signal, what is the output signal, and how the system behaves. This is not going to be possible. As a practical lab, we cannot do this, but in terms of mathematical computation, it is very easy to analyze these signals as finite polynomials which are representing the units of the control system. When we have these polynomials representing, there is an open system and closed system. We are not going to analyze whether it is an open system or closed system, but we are going to analyze how the polynomial coefficients are going to vary for these systems, whether it is an open system or a closed system. The open system can be easily analyzed, but the closed system has a feedback path which is going to give us complications. Because of this manner, we are going to convert this particular analysis as stability and polar plot with feedback control system, which is called as a Nyquist analysis. The Nyquist analysis has got steady-state measurements. We can say that it is more or less equivalent to measurement taken from instruments which are devising these control systems. So they are going to give relative stability and evaluation of the closed loop, the frequency response, how the closed loop is going to act on or act upon different kind of frequencies is called as a frequency response, which is very important for the design of any control system. With a real and imaginary complex polynomial as coefficients, and they are going to be acting as representatives of the particular control system. The polar plot is one such representation of real and imaginary plots, but in a very simple term. There is a method in mathematics called Cartesian method and polar method. The polar method can be easily suited for graphical representation, whereas the Cartesian method is easily suited for manipulation. When we take a calculator, it's going to manipulate all these polynomials addition, that is a complex polynomial, complex algebra addition in terms of the Cartesian coordinate method or Cartesian method. But when we take the graphical analysis, the graphical plot, it is going to take the polar method. The polar plot analysis is going to give us the spatial constraints concerned with the particular complex polynomial of the control system. We have the Nyquist stability criterion, which says the open loop transfer function is stable if the number of poles and the number of encirclements in a particular plane which is relating the gain and transfer function of the system is governed by a particular threshold value. This threshold is being set to 0, or this threshold is being set to some particular value depending on the root of the polynomial. This is called as a Nyquist stability criterion. The stability criterion is not well understood unless and until we look at a graph of a particular Nyquist plot. Only we look at the Nyquist plot, we have a x real axis and the y imaginary axis, but the value plotted is not just a single value as we substitute for x and y in a linear equation. The value plotted is going to be a product of the transfer function and the gain of a particular system, which is going to decide the particular stability of the control system. Nyquist design. Polar plot is a graphical representation of the open-loop transfer system. However, the Nyquist design has got a gain factor compensation. The coefficient is going to come with a product of G and H, that is the transfer function, and the gain of the system is going to be adjusted by what is called as the gain factor compensation, so that the roots or the poles and zeros of the particular polynomial lie within the stability circle, so that we can confirm and affirm that the control system is very stable. This is the way that we can say from computational numerical analysis that the particular system is stable. The stable region can vary from some plotted xy point in the real imaginary axis, and from that it can be traced into a particular curve. How the stable region varies, it can be traced into a particular curve, and along that, if we choose the coefficients of a particular control system, then the control system is going to be stable, and it will be manipulating the input signal with the stability, and it will give a good frequency response to the output. This is what is being done by the Nyquist design. So Nyquist analysis of the control system is converted into what is called as a Nyquist design. Only with the help of Nyquist design there can be a stable control system, and we believe in it. When we design based on the Nyquist design of the control system, we have the compensation method called as the lead compensation and the lag compensation. When we say lead compensation, the lead and lag of a network is mainly based on phase of the network. The phase is a term related to the time constraint of the signal and the behavior of the control system to the particular signal. Every unit in the control system is going to add some time delay to the particular signal. When the signal arrives at the output, it is going to have, because it's a feedback system, it is going to have a lag between the arrival and the input to the control system. This is the time delay of the entire control system, but this is not phase. This is not going to indicate of the phase of the system. The phase is going to contribute to the distortion of the signal in the middle of the system. This phase has to be cancelled out. It is not possible to cancel out phase due to numerical delays in the particular units involved in the control system. Hence, we have the lead and the lag compensation, which can be adjusted by the coefficients of the polynomials. The lead and lag compensation are studied by particular root values of the polynomials, which are obtained from some derivative analysis. Having seen such an Nyquist design, we are going towards the root locus. The root locus is the main concept of a transfer function analysis, wherein the polynomial takes into account accurate computation of the time domain response in addition to the available frequency response information. Time domain response information is very vital in designing this particular delay constraint or the phase constraint, whereas frequency response is very important for filtering out the noise in the entire system, or the noise that may be arbitrary to the system. when we see the different analysis from the root locus, for example, the gain factor, as we saw in the nicest design, there is a gain factor. The gain factor GH can be represented as some damping ratio divided by a polynomial with its roots solved. Instead of representing a polynomial by s squared plus 2s plus 2, we can represent the polynomial in terms of its roots and the product. For example, s plus 1 into s plus 2, that may lead to some polynomial. In this manner, the damping ratio, which is a numerator, divided by this particular product representation s plus 1 plus s plus into s plus 2, it is going to yield us some plot in a graphical sheet, such that we can see how the damping ratio is going to affect the particular area of the system involved in the graph spatial origin. The graph spatial origin is going to be a 0, 0, or it can be an elevated spatial origin from which the damping ratio is going to see, or it is going to see how the system is going to be constrained in a particular area, so that we can only operate the system within that limitation or within that margin boundary. This is being given by the damping ratio from the root locus analysis of the control system. We haven't gone into the frequency analysis or frequency plot of the control system. Frequency analysis is done as in the earlier applications, like a frequency response plot, the gain mapping, and other things. However, they are more important in the control system concepts of these design and numerical curves, which involve the phase compensation, magnitude compensation, and the pole zero approximations. When we consider polynomial in the numerator, for example, s plus 2 divided by s plus 2 product s plus 1 in the denominator, this is going to result in the number of poles and number of zeros. This particular equation is going to be represented in the number of poles and number of zeros that are going to approximate the control system behavior based on the values. Then we ask ourselves, what are these values going to be manipulated? They are directly given as a 0 and a pole in the equation itself. This question is better answered only for considering the stability of the particular system. Only for considering stability of the particular system, this question is best answered. However, when we go outside from the stability criterion of the control system, the control system entire response even can be studied by substituting the values for what we term as the coefficients, which are derived out of the polynomial systems. Hence, we can slowly convert this particular stability condition into a frequency response. This is how both plot board analysis evolved. And what we saw about the pole zero is going to derive the stability of the control system. It is now going to derive the frequency response of the system. Frequency response is still complex by substituting values for the polynomial coefficients instead of the roots of the polynomial. So root of the polynomial is analyzed for stability, whereas the coefficients of the polynomial are manipulated for the response. We have the frequency compensation, phase compensation, magnitude compensation, feedback compensation, and the cancellation compensation, which are related to some compensation analysis, which are terms given when we analyze these root poles and zeros for the stability. And it is going to be advanced for board analysis in terms of frequency by substituting the coefficients with values. The root locus has got two concepts, namely the gain margin and the phase margin. The extent to which the gain may vary in the system is determined by the gain margin. Similarly, this concept is valid for phase. The gain margin is given by the value of the asymptotic point, which is termed as a k. And only the k is given as a constant in terms of control system numeric graphs representation in textbooks or even the plots are in MATLAB. This k at imaginary axis crossover. Imaginary axis crossover is the y-axis. The axis crossover we define a point called k. From that we are going to interpolate this particular k value, how it's going to be varying along the left or right of the axis, but left of the axis is taken for the stability of the system, depending upon the sign of the particular polynomial in the system. If we have the positive sign of the polynomial, then we come to the left of the system. When we have the negative sign of the polynomial, then we go to the right side of the imaginary axis of the system. This is being done. So gain margin is equivalent to the value of k at the imaginary axis crossover divided by the design value of the k, that is the value of the k which we initially set for its design. This will give us the gain margin. Similarly, we have the phase margin defined in terms of the phase values. One may ask now, what is the need for analysis of such a system with numerical computations and some complex mathematics which are not going to yield us quickest possible value within a time. It is going to squeeze us as well as consume large amount of time if we derive mathematically and if we derive or plot mathematically. However, this is a set template. Once we do it initially, this is a set template with which the next system in the polynomial can be analyzed in slight variation with the initial system. So it is like an image with which we can compare the new image with the original image. The new images can be coming as we design, as we vary the polynomials of the system. But the original polynomial of the system we have already obtained the image of the original polynomial of the system in terms of graph. We can compare the original with the newly constructed graphs so that we can see which particular polynomial representation of the control system is well behaving or it is going to be stable as it is, and it is going to yield us very good frequency response. So this is a very big thing. It cannot be done just by looking into the images at first sight. So by practice this can be done by us. However, this is what MATLAB or MATLAB does. It compares a series of curves that are obtained from this resolution of the real and imaginary from the complex polynomials, and then it compares the system with the complex curves. We can say that the particular design or particular damping ratio can be varied for this particular system to this limit, or this particular damping ratio cannot exceed the limitation of the system. We can say that a frequency which is going to be outside the boundary is going to lack appreciation from the signal, and system gives the damping ratio. This is the product analysis of numerical methods to control system design, and we want to have some helper tools to better understand this product analysis, in addition to our work in mathematical derivations and transformations and solving complex algebra, then manipulating the complex algebra in terms of different equations or in terms of different coordinate systems, etc. Thank you very much for listening to Control System webinar and seminar.